Thermochemistry is going to be defined as the study that is concerned with heat changes that either occur during a chemical reaction or what we'll refer to as a chemical process. The difference being that a reaction is when you're producing new substances, and a chemical process can be something that's a phase change just within the same substance, so you're not actually making something new. So it's concerned with the heat changes that occur during a chemical reaction or a physical process. And so something we're going to talk about a lot here is heat. And so a concept that you need to understand right away is that there is no such thing as cold as a thing. There is heat, and then there is the absence of heat. Heat, we will abbreviate it as Q, that's the variable for heat, is a form of energy that flows from the hot object, so I'm going to use red to denote hot, or at least hotter object, to the cooler object. That doesn't necessarily mean that the cooler object is cold, but I'll still show it in blue. And then this really corresponds to the amount of energy that they have. So a hot object is going to have more energy, and the cold object has less energy. And then the units that we use for heat, typically we're actually going to measure them in joules, so that's kind of where most of our calculations will be in joules or kilojoules, which isn't on here, but we abbreviate everything as kJ for kilojoules. There are 1,000 joules in a kilojoule. But a calorie is another way that we can measure heat or measure the energy. And a calorie is the amount of energy or heat required to raise the temperature of 1 gram of pure water by 1 degree Celsius. So this definition, the ability to raise the temperature of something by 1 degree Celsius, or the temperature of specifically 1 gram of something by 1 degree Celsius, is called the specific heat. We'll use that later on in our notes on this page. So it's the amount of energy required to raise the temperature of any substance, or of 1 gram of any substance by 1 degree Celsius. So everything has a specific heat, but the specific heat of water is what we refer to as a calorie. And then there are nutritional calories, like the calories that you see on the food that you eat. One, we call it big C calorie, is equivalent to 1,000 little c calories. So sometimes on nutritional packages you'll see something that says kcal. That's the same thing. Or sometimes you'll even see kilojoules. So a kcal is 1 big C calorie, which is 1,000 little c calories. It says kcal, I guess I should say 1. 1 kcal equals 1 big C calorie equals 1,000 little c calories. So capital versus lowercase. So it technically does make a difference, but sometimes when I type it, it has the wrong thing. But this I think is alright. So lowercase calorie, and then big C, little c. Oh, that's actually what that says. And then a joule is really what we're going to be using the most. This is the SI unit for heat and energy, and then like I said, we often use kilojoules. And so just like 1 kilocalorie is 1,000 calories, 1 kilojoule is 1,000 joules. And then we've kind of already said this, but heat always flows from a hotter object to a cooler object. So I'm kind of using heat and energy interchangeably because in this unit, the type of energy that we're dealing with is heat, but it's important to note that heat is just one type of energy. And energy is really just the ability to do work or produce something. the law of conservation of energy, which, just like the law of conservation of matter and the law of conservation of mass, states that we cannot create or destroy energy, but energy can be transformed into different types of energy, and it can also be transferred between substances. So the law of conservation of energy says energy cannot be created nor destroyed. And I'll say it will be transferred and then I'm going to say and slash or transformed. 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 Okay. So energy cannot be created nor destroyed. It will either be transferred or transformed, or maybe both, into a different type of energy. So that could be like mechanical energy, or something like heat could be turned into light energy, or chemical potential energy is often observed as heat energy once it comes out. So the transfer of energy is what we're seeing. And then all chemical reactions will involve either some type of release of energy or absorption of energy. So all chemical reactions involve a release or absorption of energy. And then with those words, I want you to really start associating a positive or a negative value with them. So if you are releasing energy, would that be a positive or a negative value? Negative. And then absorbing energy means that it would be positive. So if enthalpy, which is the change in heat content, that's a way that we're measuring energy, if enthalpy is negative, that means that energy is being released, and if enthalpy, or delta H, is positive, that means that energy is being absorbed. And then this next part says thermochemical equations. You will treat heat change, which is delta H, just like any other reactant or product. So remember that delta means change. I think we've talked about delta something in here before. I just don't remember what. So anytime you see that triangle, delta means the change in something. And so when we are calculating the change, I'm going to kind of jump down here, just since we have space. Delta means change. And if you are calculating the change in something, you are always going to take your final value minus your initial value. So whatever it is, whether it's temperature or heat, or if you're talking about your bank account, or if you're talking about, I don't know, weight gain or weight loss or something like that, if it is a change, it's always your final value minus initial. And this matters because this will give you the correct sign. So you have to go in that order. If you get them flip-flopped, it will give you the right value but the wrong sign. And in terms of a chemical reaction, your final value is going to come from your products, and your initial value is going to come from your reactants. So really we can look at this as that, products minus reactants. And so I just wrote that delta means change, but we're going to use that delta symbol for multiple things. Right now it's delta H, which is the change in heat content for the reaction. Later we'll see delta T, which is the change in temperature. And so we'll talk about whether you have a positive or negative value, what that means in terms of is the thing heating up or is it cooling down. And then we'll do a lot with endo and exothermic reactions and processes. So for an exothermic process, what does that word exothermic mean? Outside heat. Yes. Okay, so outside heat, I'm going to write, I don't know if y'all will be able to see it in gray, but I'll try it. So outside, no, that is super light. Can you see that at all? Maybe a little bit. Outside heat and inside heat for endothermic. exothermic, outside heat, endothermic, inside heat. Okay, well, let's translate this into what we're actually going to be using. So I'm going to try to relate these to these words here of release or absorption. So if it says outside heat, does that sound like it's releasing heat or absorbing heat? It is releasing heat. So something that releases heat to its surroundings, now I'm actually going to change into the color that it's going to be. I tend to use red for exothermic and endothermic, and on this page it makes sense to a lot of my students, but then on the next page it really confuses y'all, so I'll just keep kind of switching around. Exothermic process is going to release heat to its surroundings. And then endothermic, I'm going to use blue because inside heat means that it is absorbing heat, so it absorbs heat. From the surroundings. And then I'm going to tie in the signs that we put here, again, just trying to get you used to seeing the types of words that you'll see. So to release heat, we have a negative sign already associated with that. Another way we'll say it is that it loses heat to its surroundings. And if you're absorbing heat, you are gaining heat. And then I have a little chart for us here talking about the direction of heat flow and then the delta H sign, what type of reaction it would be. So for each of those, we've kind of already defined it. If the heat is flowing out of the system, what type of reaction would that be? If it's going out, exothermic. So heat flowing out, another way you'll see that is that it's being released. You could also say that it's been lost. And since it is being lost, the delta H sign is negative. And then I like us to get into the habit of being able to recognize it on a graph as well. So if I had a graph to represent the reaction progress, so your reaction is going to progress in this direction, so I'll say reaction at the bottom, and then I'll put an E for energy up here. So that energy is representing the amount of heat of the reaction. As your reaction progresses, what you have at the beginning of the reaction, so this is almost like it's representing time, but instead of it being like a specific amount of time, it is just throughout the course of the reaction, however long that takes. At the beginning, the things that you have present are your reactants. So if I just assign a random value on my energy scale here, if my reactants have this random amount of energy, and throughout the course of the reaction, heat is lost or heat is released. By the end of my reaction, once you have your products, would you have more or less or the same amount of energy? Less. So your value should be somewhere down here. And then the shape of the actual graph, it actually has a certain amount of activation energy it has to overcome, and then it will sort of level out. But overall, the way that you can tell what type of reaction is happening is based on the amount of energy that you had at the beginning of your reaction and the amount that you had at the end. If your overall trend is that you lost energy throughout the course of the reaction, you have a negative delta H, you lost energy, that means that it is exothermic. So the heat of, or the energy, we'll say, the energy of the reactants is greater than the products, meaning greater than the energy of the products. But because energy can't actually be destroyed, if you have more energy when you start in the actual reactants or products, the things that are taking place in the reaction, then this tells us that heat would be released from the reaction. So what this would show is that you would have your reactants, and then heat would show up on your product side. So you would have products plus heat. This is what makes something thermochemically balanced, meaning that your reactants, they have more energy. And so, yeah, you can balance the actual elements that are in your reactants and your products, but for this amount of energy that's lower, to equal the same amount of energy that your reactants had, heat has to show up on that side. And we'll get more practice with that in a little bit. So all of that I wrote in red because it is exothermic, and when you touch something that is exothermic, typically what you're going to observe is that it feels hot because it is releasing heat. This ends up confusing a lot of students when we talk about our phase changes especially. So let's talk about endothermic. This is when heat flows into the system. So if heat is going into the system, I would call this an endothermic reaction. We've already established that the delta H value would be positive because it is gaining heat. So positive. So heat is absorbed. Or gained. So it's basically just going to do the opposite of this the entire time. So what this would look like in terms of an actual reaction like this, if we start with that part, is it would be I have my reactants, and the reactants gain heat from somewhere. So reactants plus heat, or really sometimes you'll see it just written as energy, and then it would yield my products. So in this case, heat is a reactant, and then in the case of my exothermic reaction, heat is a product. And then if I go over to draw the graph, we'll label our axes the same way. So we'll have reaction progress along the bottom. So as your reaction progresses, your reactants would be on this side, the process of the reaction is taking place in the middle, and then the end would be your products, and your energy is listed over here. So if I start, again, with just a random amount of energy for my reactants, it might be higher, it might be lower, but the important part is what the change is. We're interested in what the delta, the change between my initial and my final are. So if you are endothermic and you are going to gain energy, heat is going to be added to your system. If you start here, your final value should be higher than what you started with. And so again, the graph of the actual reaction is kind of like a little, I'm never good at drawing these. But the main part to get from this is that your reactants start with a lower amount of energy than your products. So the energy of the reactants is lower than products. And then I'll zoom that out so you can see. And then on the bottom here, it says thermochemical equations where you will treat heat change, which is delta H, just like any other reactant or product. I think I said the exact same thing up there, yeah. So, for example, if your delta H value is given to you as positive, then you are gaining heat throughout the course of the reaction, or you need to gain heat for the reaction to progress. So if I were to show where this delta H goes in terms of the equation, would it be on my reactant side or on my product side? So if we look at this, our delta H sign, if it's negative, we put heat as a product. If it's positive, we put heat as a reactant. So here, my delta H is positive, so I would put it on the reactant side. So usually it would be shown as like the third reactant on here, but I don't have space there, so I'm just going to write it out to the side. So plus 89.3 kilojoules. So it would be listed in the reaction this way. In terms of the reactions, even if something is supposed to be negative, your delta H value is what we would maybe refer to as negative, but in the actual reaction itself, we're never going to see a negative value in here. So you can determine that it's negative based on it being on the product side. So if you have plus energy at the end, you're not actually adding energy at the end. What that means is that energy is being released. And so the way that we show that is like in this case, where I have my two reactants making my one product, plus I have energy at the end. Since that energy is on my product side, my heat is on the product side, my delta H value should be negative, and so it shows up as positive just to show you that it is on this side. But then when I convert that to an actual delta H, I just say that it's negative 1625 kilojoules. And so we can ask you to do it kind of in both directions, where I can give you a negative delta H value and say, okay, if this reaction that takes place has a value, or a delta H value of negative 536 kilojoules, where would I put that number? On the reactant side or on the product side? On the product side. Since this is being released because it's negative, I would say plus 536 kilojoules. So in the reaction itself, you will always see it listed as positive, but the delta H, the negative, tells you which side it goes on. And then in this case, if I have my reactant plus heat, or energy, creating my products, is my delta H going to be positive or negative? Positive. Since my heat is a reactant, it will have a positive value. So it would be just 65.2 kilojoules.